So I want to talk about Ricci-curvature. Essentially want to talk about, we wanted to prove these entropy decay estimates, right? Log-Sobolev inequalities. That's what we wanted to do. I was asked by Ivan Bade to, there is a problem with a commutative proof. And then the first thing we do, we tried Bakry-Emry theory. And we looked at curvature. We had a lot of fun, and it was a nightmare. So the first part is about the nightmare and where things go wrong. And then I will tell you a little bit how things get better. Okay? This is joint work. So this paper is joint work with Hajouni, Nick, Ligao, and I have many discussions with Roy and Peishu, and Eva is also involved in some of the papers. So we will see.
Sorry, and who is your favorite cousin?
Huh? She died a couple of weeks ago.
Is it serious?
Yeah, that happened while I was here, and so I think we have to remember the personal moments as well. Okay, so I will give you a little bit of an overview because those who know me know that I'm like to do a little journey, right? Things are connected in my head, and I will try to share that. We will start with some classical geometry. Talk about the definition of Ricci-curvature, how it's used, abstract formulations. Then I will turn to the noncommutative setup, how we try to define Ricci-curvature, and it actually matches in the cases which we understand, which are your cases, extremely well. But I'm afraid, I really wanted to go beyond these cases, and that's where we failed, right? These cases work well, but everything else was hard. I will talk about sublaplacians and matrix algebras, where we wanted to apply that, and then modified logarithmic quantities, concentration inequalities, and then coming back to Lipschitz norms, which are closer related to the topic of this semester. Okay? Good. What was again with this tangent space? Well, I think we know what a tangent space is, right? So I'm doing a gross simplification by putting my manifold really into Rm. I shouldn't do that, but it's very intuitive, right? So then you can define what the tangent space is. You take a curve in your manifold, and you have a derivative pointing in Rm, and that's your derivative. The tangent space is a collection of all of these derivatives. Okay, I hope you have seen this before, but what is the tangent space? Right? It's a supermanifold. Yes, and it's a bundle, right, over the manifold, because for every point you have these rays of real numbers, right, or these vector space. A vector space plus a manifold, right? Sorry. That's also true, but I'm not going into supermanifolds today. A section is just a vector field. It's just a map from the manifold to the tangent space, which somehow matches the points. And vector fields can act on functions by just calculating xf of p. I'm using Carroll's method, right? Nature is better than red light. So we just differentiate the path at the point, and we're assuming that gamma of 0 is p, right? So we have a pairing between functions and vector fields. If you want to do a little bit more formal, you can say every vector field defines the derivation. Delta x of x is s of x. So, first of all, delta x of f is a function, right? We input a function, get a new function, and it satisfies this obvious Leibniz rule, right? Just product rule for differentiation is something we have all learned quite a while ago, but that's the prototype of a derivation. So I'm saying that some of the structures we want to do in non-commutative worlds has to do with derivations, right? So that's something we have to accept. If you want to talk about Ricci-curvatures and whatnot, we have to talk about certain vector bundles over the manifold, so larger spaces and derivations. Okay, good. If you have Riemannian geometry, then there is this thing you learn, right? This is just differential structure. It has nothing to do with geometry. It's just differential structure. But if you have a Riemannian geometry, there is this Levi-Civita connection, right? A connection is just a map from sections, right? Vector fields to endomorphisms of sections, saying that if you apply nabla to y in x, you get, nabla, again, this is again a section, right? So it has some rules. It is a module over multiplication with f, and here it has some kind of modified Leibniz rule, right? Here you differentiate the function, and there you differentiate the vector field in the vector field, right? So you have to understand this bilinear structure, right? So a connection sends a vector field to a map which sends sections to sections, right? I mean, just why do I do endomorphisms? Because endomorphisms are essentially, families of matrices. Look, I really love matrices. So.
But of course, you could have also done section times section to bilinear, right?
Yeah.
Okay.
Good. And so the sections, of course, is a module over functions because you can multiply a vector field with the function. And in particular, you can actually multiply derivations with a function, and that's a feature which we observe here. And we have to come back to this later. Good. Ricci-curvature. So there are many differentiation formulations of Ricci-curvature. I'm more going to the cotangent bundle. But yes, first of all, how do we get the Levi-Dirichlet connection? There's a cheating way. You write down the canonical connection on Rn, which sends dx to dx dx, and then you project it down on the tangent field. So this is the external definition, right? So you can, geometrically very easy, but there's a better formulation which is intrinsic. But we're not going to go there, right? I'm just telling you this is what we should do if you do intrinsic, but it's also not hard to visualize, right? You essentially project down twice on your tangent space because, you have vector fields here, vector fields there, and then you project, right? Okay, so Laplace-Beltrami operator, you take an orthonormal basis. Now we are giving ourselves a geometry. If we have a geometry, we have an inner product on vector fields. We can talk about an orthonormal basis of vector fields and define the Laplacian as the sum of minus xj squared. So xj is now, I could have also written here delta xj squared, right? The delta xj is an operator and we apply it twice. So it's a question of how you interpret this, but the point is this xj here is not the square of the vector field. This is viewed as the operator of differentiation, and you do it twice. So it's a second order differential operator. The geometry, because if you differentiate it twice, the geometry kicks in this first order terms, which you usually see. We have seen that in the talk, even in this. We had a talk with second order changes, right? That was you, right? Somebody worked on, right? So here it's first order changes classically, and then you can even go beyond that. We have seen that in this week, and why not? But we are doing it too simple, right? We're just staying in this category. Good. So the Ricci tensor, for me, is just a map from the cotangent space to the cotangent space, and it has a certain property. You first apply the Laplace-Beltrami operator, and then the differentiation. And you could as well have first apply the differentiation, then you apply the Laplace-Beltrami of one forms, which exists. But this is not correct. There's an error term, and that is given by a linear map on the cotangent space. This is the cotangent formulation, which for non-Newman geometry is a little bit better, but also it's also better for semigroup theory. Okay, so we have this linear map, and then this has nice applications. Oh, the Ricci curvature is positive if this linear map is positive as a bilinear form, and then this is important for W2 geometry. That's not my expertise, but I know enough that it's really important.
Yeah, can you just ask a question?
Yeah.
I'm not used to see this formulation, and I want to understand. So if I try to write more than instead of using the forms, I want to use more the classical Bochner. I will see like a Hessian kind of thing appearing, and I want to understand if it's hidden in the Laplace one.
Yes. Yes. So the connection first was defined from sections to endomorphisms on sections, but then you can extend it by some calculus to connections on one forms. So first you have to go to dual objects, but this is like linear algebra duality. You just have to be careful with tensor calculus, right? Duality involves the inner product, and sometimes the matrix goes up, and sometimes the matrix goes down. So there is a canonical choice for this differential operator on one forms. Yeah? But it's actually, we will come back to this question, so keep it in mind, okay? So one of the other applications I find super fascinating is the fact that once you have Ricci curvature, you have this entropy decay. This is related to these log-Sobolev inequalities, but I'm using this modified log-Sobolev inequalities, which in the commutative case are equivalent, but in the non-commutative qualities, at least complete log-Sobolev qualities are nonsense. Yeah, they don't make sense, but that comes later, right? But this is actually gives you in many cases the only way to calculate this constant, right? I mean, in classical cases, often the only way to get a hold on that constant is with some geometric input. If not, it gets really difficult. Anyway, so for those, since we're working in a probability space, our entropy is just this f log f. It's, minus the Neumann entropy if you want. Okay, abstract formulations for generators in general. So this is for geometry. Then particular Paul-André Meyer looked at the Ornstein-Uhlenbeck group, and he somehow formulated this whole nonsense in a completely semi-group language without referring to the geometry. And to do that, he had to use the carré du champ, which is this funny definition. And I call it gradient form because, I mean, in American context, carré du champ doesn't fly. Let me tell you, it doesn't fly. Right? It's the square of the field. Why is it called carré du champ or square of the field?
Missing one Laplacian in your formula.
I'm definitely missing the second Laplacian here. Thank you. So if you do the calculation, if this were to be a derivation, this would be 0. So derivations fall out. And if you do in a Riemannian manifold, it's nothing else but the inner product of the two gradients, right? So this is why I call it gradient form, because it's literally the form of the gradients. It's a non-commutative, or it's a generalized version of that. And the starting point of Bakry-Emry theory is to see that there is a relation. If you have a Riemannian manifold with positive curvature, then if you apply the semigroup here is e to the minus t delta, right? Then it contracts the gradient norm, yeah? So Riemann curvature gives you this contraction inequality.
There's a TT missing on the right-hand side.
There's a TT missing. Thank you. Right? So it's TT of gamma FF, right? By the way, for many purposes, that doesn't matter, but I mean, that's the different definition. But yeah, here's a TT missing. And this contraction here is given. There's a little bit of cheating. If you do the translation from differential forms, you are somehow ignoring a Hessian term. And that's a gross oversight. And that's why there is a formulation of dimension curvature theory, which is very well developed. And so here we are doing this in a sort of rough way. But it is how it started, right? So now we can talk about abstract Ricci curvature for semigroups by formulate putting the TT back in front where it belongs and ask whether that holds. And that is actually easy if you can do a change of measure. So the Ricci curvature for Rn is flat, so 0. That means no entropy decay, right? I mean, where is it? Here we had entropy decay. And if alpha is 0, then this is just the data processing inequality, and then there's nothing to say. Yeah? So if you want to do better, we have to use some tools. I mean, not we, I mean, they were used. So if you have a change of measure, you can define a new generator of a semigroup in this form. And then you do the calculation. This is a change of variable formula, which is very easy. And then the convexity of V tells you that you can write down the corresponding semigroup, and essentially you do a differential calculus, and the gradient form is preserved, but the curvature gets better if V is convex. Yeah? So for something like this, if a convex potential, you suddenly get Ricci curvature. Yeah? So that's a story. let me step in a moment. What is the problem in the non-commutative world? Let's start with a nice object. The integral becomes a trace. That's usually what we do. Yeah? A change of variable is just given by a density e to the minus something. We often call that a Gibbs state. Now, if you try to do the same game here, usually this doesn't work. You don't get a canonical generator back. The only hope that this might actually work is Melchior's talk, right? There, in some conditions, you get a generator of a semigroup back, but in full generality, if you have to do that, we have seen these extra conditions like modular group compatibility just to get even a semigroup back, right? So if you without semigroup, you cannot even talk about all these things, right? So that's one big obstruction, that some of the calculus which we use from the commutative case, change of measure, gets super more complicated and doesn't really work the way we are used to. So we have to look out for these kind of obstructions, okay? Good. So I just want to mention Paul-André Meyer because he proved this inequality again with the TT for the Ornstein-Uhlenseiter group, which is an infinite dimensional Wiener process. And that was then the beginning of, Bakry-Emry theory and concentration. And I think there's an overview of overview. I don't know how many articles you have, but you can.
And Mallet-Van calculus, which I guess was his.
Right. It's just a huge field. There's no way it can do any justice. But this observation that you have this inequality for an infinite dimensional case was also taken up by Gross, and that was super influential, right? That you can do something in infinite dimension, which makes sense, right? And the log-Sobolev inequalities follow from there. I refer to this paper by Ledoux because that's where I learned a lot of things, because I'm not able to read 100 pages, and he just writes so nice. So I'm sorry. I'm just so overwhelmed if I read that paper. It's so easy and nicely written. Okay, and he mentioned something which I find also cool. So if you have a potential, you only need convexity at infinity, because with these change of measure arguments, you can actually change. Local perturbations are irrelevant. You can somehow smooth them out. So this log-Sobolev inequalities, they essentially say that you have some convexity at infinity, and that's enough. And I find that idea fascinating. I don't know how to translate it in the non-commutative world, but I find, he got something there. He has some essential, right? Essentially that's what should happen, but yeah, okay, good. I want to go a little bit to Kahn's work because he wanted to essentially do differential calculus for non-commutative objects. So he realized that you have to talk, if you want to talk about geometry and you never talk about differential forms, you're not talking about geometry. So he worked on differential forms, and let's see what he did, right? So you give yourself an algebra. You should think of this as the smooth functions, not the C-star algebra, an algebra of smooth functions, and he defines an abstract object. Omega bullet of A sits in A tensor A is the sum of tensors where summation AJ BJ is 0. And he says, this is my abstract space of differential forms. Cool, right? Or frightening, or whatever. Yeah? Why did he do that? If we start a derivation, now a derivation is a map from A into something else. We have already seen that the something else doesn't have to be A, right? A derivation, like a connection, is a map from tangent into some larger space, so you have to do something bigger. Our next talk will use this, that A and X is not the same in a crucial way. I hope so, right? I think you cannot do otherwise. So a derivation, bimodal means you have a left multiplication and a right multiplication, and one of the important observations is they don't have to be the same. You can define the Leibniz property by just using the left multiplication here and the right multiplication there and call it a derivation. It is a derivation, and these are the derivations which we are going to use. Okay, if you take, for instance, A L infinity of V is a finite set, you can define a derivation by taking the commutator with one of these matrix units And then you will see that the left multiplication looks at the value at R and the right multiplication at the value of S. So one thing is evaluating it at S and the other one as S. Right? So these two things are different just by, and come on, I mean, this is a derivation. I mean, we write it down. You can verify these properties on the nose, okay? So derivations change. And what did he do? He said, well, why am I defining this space of differential forms? Because every derivation induces a bimodule map from this object to that object. Pi of A tensor B is delta of A pi R of B. Yeah? So this is a bimodule map now. So in some sense, the space of differential forms is the domain of universal derivations. So what are the interesting observations? If you do this in the commutative case for a differential manifold, not for graphs, because the right and left multiplication is the same, you somehow have to work not on the space of functions in two variables, you have to restrict it to the diagonal. And this restriction to the diagonal gives you very funny kernels of that map. There are kernels, these maps, these bimodule maps have kernels. And these kernels create a lot of trouble. And since you're restricting on a diagonal, we had a talk here, right? And whenever you talk about the diagonal in a commutative space, and you want to generalize that, for instance, the multiplication homomorphism from commutative to commutative, then this should be like these things. Red flag goes up. Whenever you talk about diagonal, be aware that doesn't have a non-commutative version, right? Red flag, diagonal. Here's a diagonal, so things are funny. And I asked him personally, and he totally confirmed that, right? So he totally agrees that, if whenever the diagonal comes up, you have to be very careful. Yes, and the space of derivations itself is no longer a bimodule. You cannot multiply an object with a derivation and you get a derivation. Yeah?
So why do you have this condition that the sum of AJ times BJ is 0? Like, because I feel like
it comes from the augmentation. If you write it in the group case, this corresponds to looking at the kernel of the augmentation map. So this is part of the resolution for the bar complex.
That is true. You can also just check this statement. This is one of the pages which you can read in Kahn's book. It's really on one page. You do the calculation, you see this is the right definition. Because what is the universal derivation? You send A to A tensor 1 minus 1 tensor A. And then if you do a right module, you just end up automatically. So the universal derivation is and now look what happens. If you sum them up, you get 0. And if you multiply from the right, you get 0. Since this is the universal derivation, every other derivation is a descendant of that map, plus a kernel, plus a bimodule, you're done, right? So and then you see where the mean 0 property comes from. Right? You 1 times, it's 0, right? I mean, if you multiply these coefficients, yeah? So that's the algebraic explanation. It has, I think it's an extract of many things which have been seen in different contexts. No question.
What you've written is just the map from like the level 1 part of the bar complex to the level 0 part of the bar.
Yeah. Good. What is our non-commutative setup? I think you will not be surprised that I work with the von Neumann algebra, which is just a C-star subalgebra of bounded operators on a Hilbert space, which is its own bicommutant. The commutant is the commutant, right? I mean, everything which commutes. If the commutant is self-adjoint, the commutant is automatically a von Neumann algebra. If you have a von Neumann algebra, there is something like topology. You can take trace class operators. Trace class operators define functionals just by applying the trace. And then if you restrict these functionals to a von Neumann algebra, you have all normal functionals. So we know there are good functionals and bad functionals. The normal ones are the good ones, coming from trace class operators restricted to your space. Done. We will also assume that we have a normal faithful trace. So this is another way to talk about pre-dual. we have such an element here, which tau of 1 is 1, and it's a trace. In many d by d matrices, normalized trace, we have seen this quite a bit. L2 is just the L2 space given by that trace, the famous GNS construction, which is just the completion of M with respect to this inner product. L2 times L2 is L1, da. And this, you can actually make sense of that product, and then you get the pre-dual of M. So the normal functionals can be represented with an element in L1 with respect to the trace. And L1 simply means that the trace of the absolute value is finite. Right? So all of this thing is really built like in the commutative case. You use the same words, and you just change your multiplication, and you're happy. Yeah? Good. We will not do very abstract von Neumann algebras today. We will work with d by d matrices. I'm adapting the double bar notation. We will talk about commutative von Neumann algebras, because I already talked about commutative von Neumann algebras. And we will also look for matrix-valued functions. So if you're scared of von Neumann algebras, I don't think you should be scared of d by d matrices, bounded functions, or random variables. I don't think there's a necessity to be scared about these particular von Neumann algebras. Okay, good. A semigroup, very easy to define. It's a map from M to M with a generator. I use the minus TL convention. That is debatable, but I mean today that's what I'm using. So these are normal, completely positive maps. Unital. What means unit? I will talk about normal in a second. I think so. So if you have such a generator, you can define the gradient form correctly. Here I didn't miss the second L. Yeah, it's the same definition which we just had a second ago, and because I'm using minus L, this is the right order. Yeah, what is the Schrödinger picture? If a map is normal if the dual map, right? I mean, T goes from M to M, TT star goes from M star to M star. The normal functionals are also functionals. If TT star preserves the normal functionals, then this is they are dual maps, right? And then they are the duals of these maps are maps on M lower star or L1, whatever you like. And so if these are unital completely positive maps, these are your channels, right? So standard relation between channels and UCP maps. And in some sense, I always think of them simultaneously, right? When I want to prove something, I switch to the other. I think you cannot really separate these two things. In some cases, you have to work with both of them. Let's look at an example. I told you one of my favorite matrix von Neumann algebras are the d by d matrices. I take a family of self-adjoint operators. They don't have to be self-adjoint, but for my talk, there will be, which is a cross simplification, but here they will. I can define a Lindbladian by our standard formula, which we have seen in this conference quite often. And then if you calculate the gradient form, you get exactly the sum of squares of the commutator. So the gradient form is what you expect. I mean, a differentiation is the same as commutator. Yeah? So we can always calculate the gradient form. Now, I set up an exercise, probably in one of these, if you're on a conference, you sit in a hotel room, why don't I calculate whether this gamma 2 condition, which Paul-André Maillard suggested, can I not check this for an elementary L? And then you're sitting there in your hotel room, and you try, and you try, and you fail. Right? It's super difficult for concrete matrices to look at this Paul-André version of Ricci-curvature. And that's one indication that things are different, or at least not as elementary as we want them to be, right? Non-commutative Ricci-curvature. So now here I will assume that I have a trace symmetric semigroup. I can extend this to GNS symmetric. I don't know what to do with KMS symmetric. Anyway, let's do the easy case for today. It's Friday after all. So we can find for such a self-adjoint case with some minor condition that the gradient form is a conditional expectation by some delta delta star, and the delta is a derivation from n into a larger algebra. We find this larger algebra. It's not unique. There are a million ways of doing this, but we at least find one. Yeah? So there is one. Okay, if there is one, then I can define what it means to have Ricci curvature. Delta L, delta is one of those deltas which satisfies the condition above, is L tilde delta plus R delta, right? Exactly the same form. And I don't care what this L tilde is as long as it generates a semigroup, in this case a trace preserving one. So I don't care whether it's exactly the right Laplace-Beltrami operator on differential forms. I just want to have one. Yeah, that's good enough. Yeah?
And it's still a semigroup of completely positive maps?
Yes. So L tilde is a semigroup on completely positive maps on the larger algebra. I think I did some confusion here. Let me rectify this. This is better. So I start, in this picture, I start with the semigroup from n to n. My derivation goes from n, well, in intersection some domain, to some m. So this contains n. There's a conditional expectation En. And I have En of delta star delta is L. No? That's exactly what's happening. And yes, and the L tilde, e to the minus t L tilde is a semigroup on M, the large algebra, right? Large, small. Some abstract versions of differential forms, whatever you want to do. Yeah? It's a very strong assumption. I think this can be weakened, but at least we have a definition. Let me just finish that sentence. We say the Ricci curvature is positive if, as a linear map, this is positive. Yeah? Okay.
Yeah, just is that last sentence independent of which derivation you choose?
Whenever I satisfy this inequality and I can get that one, I'm happy. So if there exists some derivation structure with this inner product being positive, I'm done. And this inner product is n-valued, right? I mean, it's not scalar valued.
Is it possible there's another derivation that satisfies the first equation, but not the second?
If you find one, I call this positive Ricci curvature. I don't care which one. Yeah, I'm flexible. Too flexible maybe, but why am I flexible? Because we can prove a theorem that whenever we have such a thing, no matter what it is, we have entropy decay with the same concept, right? So that's enough. By the way, this is based on inequality by leap, right? I mean, it's a standard inequality by leap, which we can use here. It's essentially the same proof as the classical proof, but you have to get your calculus right. Yeah, so we have whenever we have positive Ricci curvature, we have entropy decay. This is called modified log-Sobolev inequality, modified because we're using entropy on both sides, entropy decay, right? Yeah, so Ricci curvature implies entropy decay. As before, that's just kind of maintained, yeah? So that's good. Now, why is there such a long text? Well, I mean, there are many examples which have positive Ricci curvature. We have seen some classical ones. You can do a potential on Rn, great. You can do Lie groups with the Laplace-Beltrami operator. Compact Lie groups always have positive curvature. It's one of these fundamental theorems in compact Lie groups. One-dimensional semigroups with positive curvature just on R, I think they're completely characterized, if I'm not mistaken. This is known. The fermionic and bosonic examples follow exactly that picture. Right? I mean, we did interpolate between the classical case and your model. And we also learned that the choice of this, sometimes this delta is slightly modified. It's not the canonical one. You do a little trick in order to get the right R. And these little tricks you have to allow. If not, you just don't get the calculus right. So it's very, very important to note that there's a little bit of tricky things going on, where in the form, you can put some isometries on this delta, and that will disappear in the inner product. So we can be flexible there. and so on. Right, random matrix models, fermionic system, Bose system. But essentially, curvature plus Gaussian models are the only ones where we can verify that condition. Good. Yeah, so why is that not enough for me? Why do I say this is, where do I fail? Well, I fail exactly in these examples. When I start with self-adjoint operators, I define my Lindbladian. If I have such a Lindbladian, I have these vectors. I can put some geometry on top of that. Why? I take these vectors and declare them to be vector fields on the corresponding Lie. I mean, they're elements in the Lie algebra because the Lie algebra are the matrices, right? So here's a connection between group and matrices and Lie algebra and matrices, right? So the groups. So I have a natural way to call these A1 up to A1 vector fields on some group, namely the unitary group in the corresponding dimension of the Hilbert space. Yeah, there's a standard procedure. Whenever you have self-adjoint or anti-self-adjoint matrices, they correspond to vector fields. If I have vector fields, I can define derivations on this group. And then the observation is the semigroup corresponding to this L, this is e to the minus TL, and the semigroup acting on the group, they're related by the diagram. And the diagram does what I'm trying to propagate the last month. You take an observable, you conjugate it with the unitary. That is a map which sends observables, d by d matrices, to functions with values in observables, right? Because that's, as a function of g, this is still a matrix. If you do that trick, that's actually well-behaved map. It's a star homomorphism, right? It preserves multiplication. And so we can conjugate the action on the group to the action on the matrix algebra. So in a dynamical picture, all the information is here, right? You have the information. You can study classical operators, differential operators, and they give you all the information. And yeah, so if you have spectral gap estimates, diameter estimates, complete Sobolev inequalities, all of that, they go down from up to down because you have a subsystem. You literally have a system which preserves, right? The semigroup is just a restriction of the other system. And if I'm really honest, I should write here tensor identity. All the action is on the group. There's no action on the matrix algebra anymore. So we reduce everything to the group. The group has to do the work, and then the induced open system map inherits all the properties from the group. Okay, that's fantastic. It's actually a bit stronger because I do this on the first level, but I could also use tensor product representations, and they have a similar diagram. So I can write here md to the power m, have the same picture and the same properties and inherited not only for the representation, the canonical one, but all tensor products, all representations. So that's good if you want to talk instead of bits about qubits, tensor product representations. So this is wonderful. This is what I call the transference principle. But where's the problem? Well, I think I will just start with my example. We are working with d equals 2. A1 is x, A2 is y. Now we're working with SU2, or U2, doesn't matter. SU2, what is the tangent space for SU2? X, Y, Z, so we are skipping Z. So we are not talking about the Laplace-Beltrami operator anymore because we are not taking autonomous basis, we are skipping one. And then you ask for these sub-Laplacians, where you skip some of these entries, what can you say about Ricci-curvature? And it's very natural because if you think about it, if you have some self-adjoint operators in the matrix algebra, you want to do as few as possible, right? Think of control. You don't want to control everything. Controlling all self-adjoint operators is ridiculous because it's too complicated. Particularly think of, local. You cannot do all. We have to do a subset. So we will always work with sub-Laplacians, right? So we get a sub-Laplacian, and for sub-Laplacian, I had a student who didn't like geometry, and spent a year on reading the literature of connections associated to sublaplacian. There's not one, there are two. There's a zoo, and none of them gives Ricci-curvature. It's just was a complete, I mean, she learned a lot, but I mean, essentially what she learned is don't do it. That's all I can say. So this is my example. For SU2, there are definitions of Ricci-curvatures. You have two choices. Either Ricci-curvature isn't defined at all, and if it is defined, it's minus infinity at some point. So, right, so that's a no-go, right? For this subsystem, Ricci-curvature doesn't work. Good. The only good sublaplacians are given by the Laplace-Beltrami. If you restrict them to irreps, they are multiple of the identity. Very boring. Identity we don't need. We can do by hand. So this means that this whole procedure of transferring things from Laplace-Beltrami operator where I have curvature goes down the drain. You know? Yeah, I call that a little bit of a failure, but anyway. But there's a recent work by Rosé, and we have seen the talk by Daniel. They use the commutation relation, dl is ld plus error, to get Lipschitz bounds instead of log-Sobolev inequalities, and there it works. Yeah. So that's that's the but, why it almost failed us, right? Okay, good. Nevertheless, I mean, you don't give up, right? I mean, we now look at semigroups by sublaplacians, which are given by such a kernel. These are classical ones, because if I understand the classical ones, I'm done. Perfect, actually. So there you go to the literature, and what we proved is, well, let me go to the literature in a second. So first what we prove, if the kernel, which corresponds to that completely positive map, now we're talking a commutative space, we have a really good kernel. If that here uniformly is close to 1, then we have log-Sobolev inequalities. Now, the good news I think about this is we are deriving from a large term estimate a small term estimate. Because this is true for all t, for small t, right? So that's our theorem. We place heat kernel estimates instead of curvature estimates, and voila, it works. That proof was not known in the commutative case, because we had to circumvent some lemmas, which we know would fail non-commutatively. And it also works for matrix-valued coefficients. So we have the complete version, right? So it works if we tensor these matrix algebras, that doesn't change anything. Yeah? So that is the thing we proved. And then we go to the literature. Whenever the vector field generates the Lie algebra of the Lie group, there is an abundance of literature which proves these heat kernel estimates. It's not trivial. I'm not saying it's easy. It's really hard work, but I really want to use other people's hard work. I have no problem with that. I think it's good to use other people's hard work because I don't have to do it, right? So why should we not use these tools from classical harmonic analysis? They worked hard. I want to appreciate that, right? Not throw it away. Good. So that's the connection. I also formulated a matrix version for you. Let's do this on a matrix algebra, and let's give ourselves a semigroup, and now I'm using GNS symmetry. Just because, if not, I don't really know what to do. Okay, so this is GNS symmetry, self-adjoint with respect to the inner product given by the state, which I assume to be faithful and diagonal, just diagonal for writing things down in a concrete way. And then I have this semigroup, and I'm looking at a matrix. I apply my matrix to the second component. Rs is the sum over a basis, because this is diagonal in that basis. Mu r minus a half, mu s minus a half, Rs tends to tt0. That has to be close to 1. That's the 1 from the kernel from before. If this is less than 0.1, I have complete Sobolev inequalities. Yeah?
So this thing is like something like Choi matrix. Like if
that is exactly. It's a modified. I mean, this is the Choi matrix. Actually, for people who like couplings, it's the Choi matrix plus the inverse of the state map, right? It's some kind of a. This is a matrix, right? The Choi matrix is not a well, it's also a matrix. It's a state-modified Choi matrix. Can we agree on this one? It's a combination of state and Choi matrix together. The combination are these minus signs, but we have seen minus signs appearing in some of our maps before here as well. So it's very natural. This is the condition. We have this inequality. And then our result is, well, you know, so, okay, this is hard to get. But if we have a spectral gap, we have an estimate that this T0 is less than log 0.1 plus 2 times the logarithm of the minimal eigenvalue here, d, divided by square root of the log-Sobolev inequality. So that, in some cases, can be calculated. Well, if you have a hold of the spectral gap, I mean, think of graphs, you have a hold of the scatter. That is something which can be calculated, and the improvement, there have been, I have to say that similar results have been obtained by Rousset and Gao, and they're very good. Our improvement is this log. Yeah, that's it. I mean, we improved it from the log. Before they had it without that log, essentially. Yeah. So that's, and then it becomes more realistic. Yeah. Good. Yeah, an application of MLSI inequalities are concentration inequalities. Once I have such a gradient form, I can define a Lipschitz norm. That's totally obvious. We define gradient, we do it self-adjoint, right? The F star, you know, if it's self-adjoint, you only have one term, right? We take this gradient, 1/2, that's our Lipschitz form. And then we prove that if TT is trace self-adjoint, that's what we proved there, that the dual of the gradient norm, well, I mean, if you have a gradient norm, you can define a Wasserstein distance, Wasserstein 1 distance just by duality. Yeah, supremum over phi of f, C of f, Lipschitz norm is less than 1. F here is, of course, an observable. I mean, looks like a function, but it's an observable. And then we can prove that we have this inequality here. The Lipschitz norm can be estimated by the square root of the relative entropy. That's a transport inequality. The good thing is we could use a lot of help from Khaled and Maasworks because we estimate this Lipschitz norm by their Wasserstein 2, and then we are done. Yeah? But there's a little lemma. This little translation is not totally trivial. And we have also concentration inequality. So from this inequality, we can also prove that the P norm of x minus Ex is less than the Lipschitz norm. And here I have to, this somehow flipped a little bit. So I would love to put here an arbitrary phi. I cannot. I can only take phis which are invariant under the semi-loop. So it's a what we call a conditional inequality, right? Because if we could do every phi, this would be fantastic, but at the moment we can only do those which are invariant under the evolution. So invariant under evolution, you know, whenever you have a semi-group, you have, in this case, you have an expectation on the fixed point, and then you have to take those states which are left invariant by the evolution. Yeah? So for those, this works. Remarks. Yeah, this is a P infinity, because the gamma norm here is defined, that's the infinity norm, right? Once you have a gradient form, you can not only define infinity Lipschitz norm, you can, I mean, if you have a norm, you can define everything. So you can define PP Poincaré inequalities. That's the work Joel had done. And what I'm trying to do in this time here is to teach my students how to generalize them to matrix algebras for arbitrary GNS symmetric. I'm confident it works, but it's not written down, right? But I'm very confident this will turn out, and it's nice and useful. I can go from Lipschitz estimates back to transport inequalities. So the hard part is to prove transport inequalities imply concentration inequality. I have to admit that the proof we wrote in 2018 is spotty at best, and we are writing a new paper to actually make it more rigorous and more correct, which is a good thing to do, because the proof was not really readable, not even to me after a couple of years. And I'm actually read there. But this year is also interesting. So the square root of P seems, this equivalent between transport and concentration at the moment only seems to work on the square root of P level, and unfortunately not on the P level. That would be fantastic, but I don't know how to do it. Okay, so there's some magic about the square root of P. Yeah, connections. Yeah, let me say that. Oh yeah, this is what I want to say. So, of course, if you have a Lindbladian, you have a natural choice of Lipschitz norms, which Pace you discussed. Just take the supremum of the commutators. That's related to De Palma's work. and you have a trivial estimate, you just count the number of generators. And then this Lipschitz norm is smaller than that new Lipschitz norm with the constant square root of m. What I said is this is optimum, this is usually the best. And then, yeah, if you take for the generators to be the xj's, I think they have been lost. So if you take for the aj's all the Pauli operators, xj, then there are exactly n of them. So you have square root of n, and you get an estimate n, and that's optimal. So this abstract approach to get an upper estimate on the diameter with order n is sometimes best. And this I already said. Yeah, we get Talagrand's inequality for this particular semigroup. Matrix value Talagrand inequality, that's the concentration inequality, it's a generalization. And yeah, we use these estimates. Essentially what we used is we looked at this gradient approach to find lower bounds for simulation cost by relating these Wasserstein distance to simulation cost. And the only main important lesson we learned is, well, you know, if you take this Lipschitz approach to get a lower bound, you just have to find the right observable. That gives, right? I mean, what's good about this? You find the right observable, and then everything else has to work. And this guessing game of finding the right observable to lower bound the Lipschitz norm of two states, that in some instances works out. There's no general formula. It's just in the instances where we understand it, it works out. Okay? There's a little connection to what we're doing right now. If you have self-adjoint operators, you could define a new Wasserstein distance by looking at some kind of Lagrangian form where you allow all passes which are given by commutators, ht, in time. So these are time-dependent Lindbladians, but simple ones. And the ht should be linear combinations of the given set, right? So that means you can rotate your density only in certain directions of these unitaries. That's a kind of a control approach. It's a very natural distance. It's maybe too rough because if they don't have the same eigenvalues, they're not related. But anyway, it does connect to what we're doing here because this gradient form Wasserstein distance is a lower bound for that one. So same as I said before, I can now lower bound this really complicated infimum because I don't know what is the best path by finding a good witness and guessing why they should be far apart. So the philosophy of using these gradient-induced Wasserstein distances to find lower bounds for some other ones, I think that's still a valuable idea which we should explore.